Beyond the self, avatar anthropomorphic fidelity and calibration effects on judging others' interpersonal horizontal reachability in VR. Immersive displays introduce well-documented perceptual distortions, including depth compression arising from accommodation, Vergence mismatch, and restricted fields of view. Yet little is known about how these distortions affect allocentric judgments of others' action boundaries. So we ask, can users in immersive virtual reality accurately perceive a virtual other's critical reach boundary, and which design factors shape these judgments? Drawing on two factors that have repeatedly emerged in self-affordance literature, calibration and visual body representation, we examine how each factor and their interaction influences interpersonal affordance perception in immersive virtual environments. We operationalize this as a positioning task. Participants were instructed to position an object that we call the decision object at the perceived just reachable distance, JRD, of the actor. Just reachable distance was defined as the distance at which the tip of the actor's extended right-hand middle finger could touch the decision object when reaching horizontally without bending or rotating the torso while standing behind the marked floor line. Given that task, we used a multifactorial design. Virtual human or virtual actor fidelity was manipulated as a between subjects factor with 3 levels: end effector only, a highly abstract representation consisting of floating hands, ankle joints, and a head; low fidelity virtual human, a minimal body representation based on Runzen et al. Vichur's design principles, providing essential visual information for interaction while omitting detailed anthropomorphic features; high fidelity virtual human, a gender-matched Ready Player Me avatar, selected through a pre-experimental validation procedure to ensure unambiguous gender cues and racially mixed appearances, thereby controlling for potential race-based bias. We manipulated several within-subject factors. Participants completed the task across 3 phases: pre-test, calibration, and post-test. Within each phase, we varied the virtual actor's height, the object's lateral position relative to the actor, and the direction of object presentation, either moving toward or away from the actor. In total, this resulted in 90 trials per participant. In both the pre-test and post-test phases, each trial began with the actor and decision object appearing according to the condition. Participants moved the object toward or away from the actor using the controller buttons and confirmed the trial once the object reached the perceived reach boundary. In the calibration phase, the task looked the same as the pre- and post-test. The key difference was feedback. After placing the object, participants triggered the actor's reach and received categorical feedback on their judgment. A green object with an audio cue indicated a correct placement. A yellow object meant the object was too close, and a blue object meant it was too far. Importantly, we did not provide numerical error values. Instead, participants inferred their error by seeing the object relative to the actor's reach, which mirrors how calibration happens in the real world. Participants were encouraged to move the object back and forth to explore the boundary before confirming their response. We manipulated actor size using 5 virtual actors whose heights were systematically varied around a reference height of 1.69 meters, based on average US adult height. Actor heights were scaled in 10% increments, ranging from -20% to +20%. We measured perceived just reachable distance on each trial as the exposition of the decision object. Using the actor's anthropometric reach as ground truth, we computed estimation error for each phase as perceived minus actual reach. Positive values indicate overestimation and negative values indicate underestimation. This allowed us to compare baseline, calibration, and post-test performance. First, participants completed a brief pre-immersion setup, including demographics, VR experience, headset calibration, and task familiarization. Next, they entered an immersion and acclimation phase, where they were seated with feet unsupported and saw no self-avatar, only controllers, to emphasize allocentric judgments. Virtual eye height was fixed to a reference value across participants to ensure consistent viewing conditions. This was followed by the experimental phase. Building on prior work in affordance perception and VR, we tested 4 hypotheses about judging other people's horizontal reachability in immersive virtual environments. H1. Users are able to estimate other actors' horizontal reachability in IVEs. H2. Users can improve their interpersonal horizontal reachability estimations via calibration in IVEs. H3. Actor visual fidelity impacts interpersonal horizontal reachability estimations in IVEs. Higher fidelity representations are expected to support more accurate baseline judgments by providing clearer anthropometric information relevant to reach. Finally, H4. Actor visual fidelity moderates the calibration of interpersonal horizontal reachability estimations in IVEs. Richer visual representations should support more effective learning from feedback. Hypothesis 1 asked whether users can estimate another actor's horizontal reachability in VR. In other words, whether they make allocentric judgments that scale with the other person's body size. To test this, we look only at the pre-test and analyze the perceived just reachable distance. This plot shows a clear, consistent pattern. As the actor gets smaller from actor 1 to actor 5, participants place the reach boundary progressively farther away from themselves. That's the signature of allocentric scaling. Participants are using the actor's body information rather than relying on their own reach. Quantitatively, across the full-size range, the judgment shifts by about 0.29 meters, roughly 11.4 inches, from the largest to the smallest actor. The mixed model also shows substantial explanatory power, with marginal R-square around 0.21 and conditional R-square around 0.33, indicating actor size meaningfully predicts these judgments while capturing individual differences. In post-hoc comparisons, most sizes are distinguishable, except actor 2 versus actor 3, which is just above significance at p equals 0.058, suggesting that under our viewing conditions, some adjacent size differences may be near a perceptual threshold. Overall, this supports H1. Users can judge others' reachability in VR in an allocentric way. Hypothesis 2 asks whether users can improve their judgments through calibration. We analyze signed estimation error, where positive means participants are placing the object too close to themselves, so they're overestimating how far the other actor can reach. In the pre-test, before any feedback, we see a clear baseline bias. Participants overestimate others' reach by about 0.16 meters, which is roughly 6.3 inches on average. The key result is the pre-to-post comparison. After calibration, signed error decreases by about 0.11 meters, around 4.3 inches, and also that phase effect is highly reliable in the mixed model, with TI equals to minus 17.87, and P is less than 0.001. If you translate that into where participants land, the remaining post-test bias is about 0.05 meters, roughly 2 inches. So calibration doesn't just change behavior during training, it carries over to the post-test when feedback is removed. So the takeaway for H2 is that calibration works for interpersonal affordances in VR. The simple directional action outcome feedback is enough to substantially reduce systematic overestimation. H3 tests. Whether avatar visual fidelity changes initial interpersonal reach judgments, so we focus on pre-test signed error before any calibration. In our LMM, fidelity is not a significant predictor of pre-test error and does not survive model selection, so H3 is not supported, and that also rules out the specific directional sub-hypotheses. Our interpretation is that, at baseline, participants are making allocentric judgments, but they're driven by coarse body information. The extra detail in higher fidelity avatars doesn't translate into better accuracy until feedback enters the loop. That leads to H4 asks whether avatar fidelity moderates calibration, meaning whether the final calibrated accuracy differs depending on how the actor is represented. Here we look at the post-test signed error by fidelity. We find a reliable difference between high and low fidelity. The low fidelity condition ends with lower overestimation error than high by about 0.0228 meters, which is roughly 0.9 inches, and that contrast is significant with P equals 0.0107. However, we don't see a significant difference between high and end effector, and the low versus end effector comparison is also not significant. So fidelity doesn't produce a clean ordering where more fidelity is always better. Instead, what we observe is that fidelity affects the post-calibration endpoint in a selective way, primarily separating high and low, while earlier during calibration, the trial-by-trial learning didn't differ by fidelity. That's why we describe H4 as partially supported. Representation can shape where people end up after feedback, but not in the exact pattern we predicted. To wrap up, users can judge others' reach allocentrically, calibration reliably improves accuracy, and fidelity matters mainly in the post-calibration outcome. The design message is simple: build feedback-based calibration into social VR when interpersonal reach matters. Thank you.